we just did some exercises where we reduced the noise in images that we had intentionally added. Now here we have an exercise where we have an initially noisy image, and after we average the images by having 10 different noisy images, the noise level, it is going to be decreased by a factor of 1 over the square root of k. 1 over the square root of k is going to be 1 over square root of 10, and then we're going to have 1 over the square root of 50 is going to be a factor of 0.14. So this is how the standard deviation, it is going to be reduced. So what this means is that if we have a sigma which can have 64 different intensity levels, if we average this 10 times, then we are going to get from 64 different intensity levels, 0.3, we are going to get 20 intensity levels, so plus minus. So in the example we showed in the previous session, we used an averaging over 100. That means that if the noise, the Gaussian noise that we had in the system had, let's say, 100 intensity levels times 0.1, we would get 10 different intensity levels. Here we have these examples, so where we have generated images. I think we looked at these before. So if we look carefully, I believe I had these numbers, but I was trying to reproduce them once again. So when the variance is equal to 0.1, that means that out of 255 possible values of the intensity, we have plus minus 25 different intensity levels. When the variance is 0.03, that means that we take the square root of the variance, we get the sigma. The sigma, we multiply this with the total number of possible intensity values. So the sigma is going to be plus minus 44. So when we're trying to evaluate using human perception the values, we just gave a rough number of around 50, but it's so I believe once you study for this course, you go over these slides, these are more correct. And here we see, this is really important actually, this information and this information, so you should quantify this one carefully. Okay, so let's continue. Again, this is another example. We have an image which is all ones, or actually image I1, it's equal to 64. The intensity is 64. I2, it will have an intensity around 192. So that's why where we see those, we add Gaussian noise to both of these, and the images or the pixel intensities, they will have a specific distribution around the 64 and the 192, whatever it is. Let's move ahead. So this is the code that we used. These are the results. So if we have an initial random noise with a variance of 0.01, that means that the sigma is going to be the square root of 1 over 100, because variance, the square root of 1 over 100 is equal to 1 over 10. So that means that 1 over 10, that is sigma, yeah. So let's use this expression here. We said 0.01, that means 25. Okay, so here, for a variance of 0.01, we have sigma is 25 different pixel intensity values. If we average by a factor of k equal to 10, this is the histogram we get. 500, we get a much narrower. 1000, we get a much narrower. So it is what I want from you. I really want you to carefully understand or fully understand how the variance is related to the sigma and how it is related with the different levels of intensities, okay? And how this number of intensities decreases as we are averaging those. Now, let's continue again. Here we see an image. We have two, let's say, we can have a pair of images that we want to distinguish key elements. But in order to distinguish key elements in an image, we can take the difference between these two. And here we have an example. This is not very Wait a second. Here, this is also the difference that one can obtain if we can subtract an image which has a resolution of 930 dpi minus another image which has 72 dots per inch, and we can observe. Actually, we can hardly observe, but we can notice some differences whenever we subtract these images. Human perception, we might uh, even in the second and the third image, we might have more pixels that are different, but that's all that we can perceive. Now, so let's see here. So that's one trick that we can use when we try to enhance two different images. So we have this original image which is at the top, which is the image of the head, including also the blood vessels, and we have another image which is used with contrast liquid. This contrast liquid is just a contrast which goes through the blood vessels, and since this blood vessel, this contrast goes through the brain, only using the since the contrast material, which is like a dye, është bojë ajo. Është një bojë e cila është fluorescente që kalon në enë të gjakut dhe kur bëjmë imazherin, ajo përforcohet. Dhe ne për dalluar se ku janë enet e gjakut, ajo që mund të bëjmë ne është thjesht mund të marrim diferencën e imazhit që quhet mask image, IMJ. Kurse imazhi me kontrast është II, me live image, IL, apparently that's live, and then the difference between the two, it is IM minus IL. And then, let me see, minus, and then we can have an enhanced image, which is IM minus IL. But here there is a mistake, I'm afraid. So this is the difference. IM minus, yeah. This is just to enhance specific regions in an image. Now here, another important aspect that can be done is having a specific shading, which or an illumination which is not uniform. Now, so what this means is that one edge of the image can be brighter, the rest is darker, and in order to analyze this image, what can be essential is that we want to do an uniform illumination, or uniform illumination all across the image. And for this, we have some operators, of which we are going to provide it a few slides later. But the image on the very left side, it is non-uniform. We can obtain the background light, which is the middle image, and then we can divide the original image by the middle one, and finally we can get the image which is on the right side, which now it has a uniform illumination all across the image. Now, here we see actually different types of approaches which can be used in X-ray images. So what we are showing here actually is just that whenever we try to determine some regions that we are really interested into, we can define some region of interest mask, and this mask, what this in principle is multiplication by 1 in the regions that we want to see or to enhance, and we multiply the 0 with 0 all the regions that we are not interested. So this ROI is simply region of interest. So the image on the very left side is the original image. The image in the middle is the mask, the region of interest mask. The very one on the right side, it is the mask multiplied with the original image. Now, we talked before about the different possible set operations that can be used when we are dealing with images, and some of those, they are union, intersection, associative laws, or De Morgan laws. And in order to describe these operators, we can use these Venn diagrams, where we can see, for example, where is the region A, the A complementary intersection of A and B, and many more. Now, other set operations that we can use, we can see this in here. So we can have an original image, and then from this original image, we can find the complementary or the negative of the image, and then in order to see specific elements, we can find the union of the image A plus a constant image to see an enhancement of the regions that we are mostly interested onto. Now, this is just a truth table of which we can we just see the and then ors, which we know, but the implementation of these and then ors operators, they can be shown here. So, for example, if we have B1, which is a white object on a black background, the not operator is just going to be the negative of this one. And negative in different programming languages, this not operator, or it's simply a logical operator which has some notations. I think MATLAB has a wavy feature, or sometimes I forget this. And the not operator, you can also calculate it just by assuming that from an image, the negative is also found like 255 minus the image itself. Because if you do 255 minus the image, imagine if you have some pixels that have intensities of 0, 255 minus 0, you immediately you get the maximum possible intensity, which means the dark is now going to be the brightest spot. Now we can see also some, here we see some applications of how we can find the negative. The code for this one is going to be the following. So I think we mentioned this one. We said that you can read an image, then we can find the negative as 255 minus I. Then we can show the figure here, which is the original image, and the negative of this image is going to be whatever we see in here. Then we can use averaging, and but averaging, what is interesting is that in this case, we have an original image which has a high contrast. And then we can use averaging, and the averaging, it is a linear operator which decreases the contrast, or it diminishes the contrast at the edges. Whenever we try to, let's say, whenever we try to analyze an image, we like high frequency components. And the high frequency components, they are mostly at the edges, okay? Because you have an immediate change of the intensity, so that's high frequency components. Averaging destroys it, and it has a bad effect. But this averaging, this can be used for using an intuitive approach to enhance the image by simply using addition. So what one can do is that you can have the original image, you find the average, so you diminish the contrast at the edges, and then just by subtracting these values, we can enhance the edges, but this one, we're going to present this one in chapter 3. Now we have also some linear transformations which can be applied onto the images, and these operators or these transformations that we can apply, it can be identity transformation where nothing is changing. We can have a scaling or reflection of the image. So we can have here the scaling factors. They can be Cx, Cy, and the value for Z, it can be the same. We can rotate an image using rotating matrix. And the rotating matrix, it has a form as shown here. We can have a translation over a matrix. So for all of these, we can write down the codes and implement these. We can have a shear, and a vertical shear, and also a horizontal shear. So here there are just some examples where we rotate a letter or a component, which in this case is an image. And one thing that we can notice also is that when we rotate an object, it is hard to draw a continuous line. So it's easy to draw a continuous line over an array of pixels, but it's harder to draw a straight line when we have a slope. Okay, so you see an pixelated image which has not very good details. Now, here, this is how we can show the rotation of a specific image. And now these operators, especially the shear that we see here, the horizontal shear and the vertical shear, including also rotation, these are very useful in case someone wants to implement deep learning algorithms on a specific data set. Now, deep learning algorithms, computers, they have a capability, or they need, in order to apply some deep learning approaches, we need a very large amount of images to do the training. But when we have a large number of images to do the training, if the number is small, computers can memorize all the images. So if it memorizes all the images, it's a bad thing. Now, memorize, we are kind of, it is something equivalent to that. So we want to bring some randomness in the problem. One way to do this is to increase the number of images in the data set as much as possible. And if we don't have enough data, what we do vertical shear or horizontal shear, which is going to change slightly the shape of a specific object, but anyway, it is going to produce for us a different image. Let's say that someone is trying to use classification of the houses, what a house looks like. Now, if you use horizontal shear or rotation or vertical shear, it is still going to be a house, but you may assume as if this is the angle that you took the camera, it was different. Anyway, it will be an extra data set in your another image in your whole data set. Another trick is also rotation. Rotation is very tricky because you have an original image at a specific angle. What you can do is that you can regularly rotate it by 1 degree. So you can have from one image, you can generate 360 images. So that means that the number of data set, it has increased considerably. Now here we see, for example, how we see another aspect which is essential, which is the image registration. And for the image registration, what we can obtain is that we can get the second image, which is the B. We can obtain the image C, and then after we do the registration, we can check how much difference there was between the original image and the registered one. So image registration is essentially trying to figure out where are some points or essential points which can be used as an XY coordinate, as zeros, so that you can recenter those. Now, we're going to give examples about these. Now, let's move a little further. Here, we just talk about the images that we can often obtain. They can be color images. And these color images, they are composed of 3 different layers, which will be the RGB, the red, green, and the blue. And each value of red, green, blue, they come up with a vector. Okay, so the same location of the matrix is going to be different values. Now, overall, whenever we are dealing with linear transformations on specific images, we can have transformations both in spatial domain or in the real domain, and also in the complex domain or the Fourier domain. The Fourier domain, it is, we may assume that we are talking about an equivalency between the frequency of a specific image. Now, we can pass a little faster here. So here we see an image which has some pattern structure, which is shown here. This is a picture in the moon or some. And if we calculate the Fourier transform of this image, we see the image which is on the top right side. We see 2 bright spots. These 2 bright spots, they correspond to the frequency components. And what is also essential here is that the specific, so if you see the image A, it has some grooves or some lines at a specific angle. The Fourier transform, it's these 2 dots which are shown with the help of 2 arrows. I wish the arrows were not there because they might be also confusing. If the lines in the image are rotated by an angle of 10 degrees, also the lines in the frequency domain, which are 2 bright spots, are also going to be rotated by the same angle. Now, what can be done here is that in the frequency domain, we can filter out these two frequency components by multiplying by 0 these two bright spots. Okay, so if you remember, when there was an image with dental, the teeth of some patients, we had some masks which were multiplied by one specific regions. Here, if we want to modify an image in Fourier domain, we multiply by 0 wherever the frequency is. If we remove that frequency in the Fourier transform domain or in the complex domain, we can come back to the real domain to obtain the image at the bottom part. But this one, I'm very much interested into this, especially working in the Fourier domain. So in the future chapters, we're going to talk about this one in detail. Now, here we can also talk about the different probabilities when we are working randomly with data, but we can just pass this one. And here we have also, we can have a look at the histogram, but now we have quite a few of experience with the histograms, since we did the examples of even averaging out to remove the noise. We see the image on the top. It has it has a region which is 0. If you notice that 0, that means that. So actually, let's have a look at this slide. The square, it has we divide it in half. Half of the big square is region 2. Half of region 2 is a quarter, which is equal to region 1. Half of region 1 it's an eighth, është 1/8. Pra 1/8 e imazhit është zona që ka pikselin 0, që quhet zona 0, dhe kjo është 1/8 është e barabartë me 0.125. Pra probabiliteti 12.5% e pikseleve që ndodhen në këtë katror këtu e kanë vlerën 0. Njëkohësisht ne kemi 1/8 e imazhit që është shumë, it's very bright. Kjo që është very bright, kjo do thotë që është prapë 12.5% se është 1/8 ajo. Ndërkohë, ajsa që është 1/8 shumë e zezë dhe 1/8 shumë e bardhë, kemi rajonin e cila është indeksuar me numrin 1, dhe kjo është 1/4 e imazhit. Duke qenë se kjo është 1/4 e imazhit, probabiliteti për të pasur një pixel intensity, ajsa është zona 1, është 1/4 është 25%, pra 0.25. Ndërkohë kemi edhe imazhin që është zona 2, e cila është gjysma e imazhit në total, dhe do thotë që 50% e pikseleve ka një vlerë që po e quajmë si zona 2. Ndërkohë kemi edhe një imazh këtu, i cili është një figurë diku në kuzhinë, dhe intensiteti ose histogrami i këtyre vlerave është siç tregohet në figurë. Tani, histogrami, analiza e histogramit është shumë e rëndësishme, pasi për shembull kemi në këtë rast kemi një histogram i cili është shumë i ngushtë, është simetrik. Kemi figurën e mes, është një histogram i cili është simetrik, por nuk është aq i ngushtë. Kemi edhe histogramin tjetër i cili nuk është simetrik, pasi ka një skewness ndryshe nga 0. Dhe këtu për shembull it is worth looking at the average values which are shown. Për shembull, vlera mesatare e pikseleve është 20, po shikojmë të centruar te 20 për figurën e parë dhe të dytë. Për figurën e tretë vlera mesatare e pikseleve është 8.9, ndërkohë varianca, që është sigma katror është 1 në rastin e parë, është 25 në rastin e dytë dhe 17.2 në rastin e tretë, e kështu me radhë. Në fakt këto janë moments. Pra për shembull, kjo e para, sigma, është momenti i parë ose momenti i dytë. Momenti i tretë është skewness. Momenti i katërt, që është mu-ja, është 3.0. Dhe nëse shikojmë pak me kujdes, ky grafiku i parë, në që gjatësinë e boshtit nga ana djathtë e nga ana majtë ka të barabartë, the third moment, që është mu-3, është e barabartë me 0, kurtosis është 3.0, sepse është goxha i egzageruar. Atëherë vazhdojmë këtej përsëri. Këtu kemi këtu për shembull kemi rastin e një imazhi të cilin ka një histogram që është i alokuar kryesisht për vlera të mëdha vlera të larta të pikseleve, që do thotë it's more bright. Ajo që mund të bëjmë ne është që ne histogramin mund ta shpërndajmë ose mund ta barazojmë. So this is called histogram equalization, and whenever we have histogram equalization, that means that we can obtain a relatively comparable number of dark pixels with a comparable number of bright pixels. Now, we can also talk about the probability density function, and we have the cumulative density function. We can have this probability density functions. We have that in all of the histograms, the integral, I think we have mentioned this quite a few, is going to be equal to the probability density integrating over delta z. Now, this was something that I was trying to show in the previous session, but this is better represented here. So the percentage of the data which can be found from the center plus minus 1 sigma, it's equal to 68.2%. The percentage of the data, so which is plus minus 2 sigma, is 95.4%, and the percentage of the population which is found between plus minus 3 sigma, it is 99.7%. So I was wrong before I said it was 99.5, that's what I remembered. But apparently it's 99.7%. And as an example, let's say that if this average value is, let's say, the density of the bones, what happens is that in cities that have a high humidity, the density of the bones of the citizens is very low, and this is a sign of osteoporosis. We never wish this to no one, to anyone, but this osteoporosis, the density of the bones for all the population of the world, it can have some specific values. If the density of the bones is very low, that means that a patient can have a score of minus 3.5 sigmas. That minus 3.5 sigmas, you can easily see where the density is going to be. Okay, so it's going to be out of the 99.7%. Okay, which means that it's 0.3% divided by 2 is 0.15%, because half of that is for sigma for people that have a very high density of the bones, which are 3 sigmas more than the world average, which is very rare case. I believe you have more people with low density of the bones than people with a very high density of the bones, because people don't develop high density of the bones as they age. They only deteriorate. Okay, so here we see again different types of Gaussian distributions. Here we have a Gaussian distribution in 2 dimensions, which are shown here. This is again random Gaussian distribution, which are, as we can see, they are denoted here. And what we can notice also here is that we have an equal variance along the x-axis and an equal variance along the y-axis. In the second representation, we have a different distribution along the y-axis and a different distribution along the x-axis. And here we observe another matrix C, which is 12, 6, 6, 5. Now, whenever you see this matrix, what a student that has taken linear algebra should immediately do, and you may try this one as an exercise at home, is the following. Diagonalize this matrix. So you have a matrix which is 12, 6, 6, 5, okay? Diagonalize this, and then after, this would be even a good homework so that we can go over this material. So this is slide 45, so you can take a note here. In slide 45, given a matrix which is 12, 6, 6, 5, find the eigenvalues, so that means that find lambda I, find the diagonalizing matrix, and find also the eigenvectors, okay? Now, the eigenvectors that you are going to find, most probably, are going to be the direction of how the randomly generated points are distributed. Now, here we see some examples. Let's see what we observe here. Here we see an image which has some biological sample. So these are cells, and this is an image which is approximately, let's say, in the order of 1,000 by 1,000 pixels. And what one can do is that we can crop. So what this line of code here is doing is selecting the first 200 rows and the first 300 columns. So this is what you obtain. And this one, it's 200 rows, so that's why it is narrower and it's also wider. So having this image, this is what we see here. But now assume that we want to have a larger image for some reason, where one of the major reasons it could be the following. So for example, if we want to count these objects or these structures that we observe here, some neural networks, they perform very well. Some don't. There are also some neural networks, or convolutional neural networks that perform better on larger objects than smaller objects. This is in the literature. You can find papers that do this. In this case, what can you do in this case? If you have a certain convolutional neural networks which performs better on small objects, what you can do is that you blow up the original image like this one. So it was 200 by 300. We just blow up this one, which is this I small. We expand this to 400 by 400 using bilinear interpolation. So linear interpolation, it's a good way to fill in for the new pixels which are going to appear in the modified image. Okay, so here we can, this is just an exercise of which we can run the code and see how this can develop. So originally we have apparently with this image of the cat, we can add noise with a variance of 0.5. Here we can add noise with a level of 0.01, and it looks like we have less and less noise. This is the same image of this animal, but in grayscale. This is adding noise in grayscale. This is adding noise again in grayscale with a different variance. Now this is the code that we can run all together, and so checking the effect of the noise. I think going over the code, it might be more smarter because you can observe what we are seeing in detail. Now, this is, I believe, let us see. Okay. Now, what could be, let me see for a moment. How is it possible that I should be presenting because I'm not using the board. Okay, so this is, so this PowerPoint, it was the correct one then. Or not, the PowerPoint is better actually, and sorry, the PDF it was better. So actually this is all we want to say regarding chapter 2. I want you to go over these, and the most fundamental aspect is the issue of the noise and also the interpolation, including motion, let's say how we call this, the shear, which means that we can just change slightly the shape of the image. Yeah. Now this codes that we have them here, I don't want to run them now, but you can experiment yourself. But sorry. I strongly suggest you to go over these. So for example, we have this example of the cat. It can be any image. It doesn't have to be the cat. Or I can have a look at the example of the cells. There was an example where we used the bilinear extrapolation. Or here, this is a good exercise. So let's clean something out. Now, in this exercise, but we can also leave this for the next session, we observe that we can read an image I, and this is the image, okay? So this is the image which we should expect to see, but in fact, we don't really see much. But if we insert here data cursor, let's see if we can read different values. So this is 0.01. So this is 0.0078, 0.02, 0.03. I'm just trying to read the values on the monitor, but I'm afraid you see much less. And the pixel intensity distribution, which actually here we don't see much because human perception does not do a very good job by changing the pixel order values in the darker region. And apparently, these are some images obtained by electron microscope. The intensity and the contrast is very low, so that's all we can see. But one thing that we can implement here is that we can multiply. So let's see, I1 is the image, okay? So this I1 we can multiply by 10, and we can just do this operation. So we found I1 multiplied by 10, and this is all the same. Okay, so this is the new image once we multiply by 10. So this is the original image that was obtained from the microscope, but the contrast was too low, and this is what we can observe. The computer can see this perfectly. So what we see here is this. And then we can also plot the histogram of this image, which is multiplied by 10, and we observe that the histogram is going to be like this. Originally, the histogram it was like in here. So all the pixels they were in the darker region. So and then we could see nothing. Then we multiplied everything by 10. So this histogram it all shifted to higher values where human perception can do a good job, and that makes it possible for us to see the image that we just had a look at. Now, this is just a very simple approach of how to enhance this image and to make it possible for us to observe something. Now, something extra which is in this image is that we see some regular patterns which are all across the image, and there is a way to deal with these. And when we say a way to deal with this is that we can try to completely remove this noise or this periodic noise using the modification or linear transformations in the Fourier domain. Okay, so you have these codes. Maybe I have to include also at least this image, which looks like this. You don't have such an image. I may include this one in the files of the course, and you can play with these. Now, if you like, we can have a short break.